Welcome, everybody. Thank you so much for joining us. We really appreciate your attendance today, and we're looking forward to a good discussion. My name is Becky Oler. Hold on. I'm just going to, Christian, I'm just going to mute you. I think I'm hearing myself. Or maybe, oh, you've got it. Okay, great. My name is Becky Oler, and I'm the Sustainability Manager at Impossible Metals. Today, I do have a small part in one of the presentations, but primarily I'll be acting as facilitator today. And so first things first, I've got some housekeeping to review. So please mute your microphone unless you're speaking. During the discussion section, there's an option to do a hand raise here in Google Meet. So of course, you're welcome to speak during that time. And we'll just ask that everyone else keeps themselves muted because you can get that feedback. The meeting is being recorded and a meeting summary will be created. Input and responses from this meeting will be recorded in the updated EIS. So if you provide input today, you don't have to also submit it in writing. You're more than welcome to, but that input will be recorded as part of consultation on the EIS. We do ask that attendees use respectful language toward one another and the host at all times. There will be a facilitated discussion after the it says after the webinar, but it does mean after the presentations, not after the webinar. You're welcome to add questions or input to the chat during. So you'll see there's a little chat box, and you can add questions as you think of them, or you're welcome to hold them until the end. In the chat or when speaking, we would really appreciate if you could introduce yourself, and if you're associated with an organization, speaking on behalf of an organization, it'd be great to let us know that as well. It's for the purpose of reporting into the EIS. And you may also indicate if there's a specific person that you would like to respond to your question. So at this time, we do have a small addition to our agenda this morning. It'll be very brief. And so I'm going to pass things over to Jason Gillum, who is the CTO at Impossible Metals.
Hello, everybody. As Becky mentioned, I'm the Chief Technology Officer and the Chief Operating Officer here with Impossible Metals, and just have a brief postponement announcement to share. As part of our commitment to transparency, we want to share with stakeholders that Eureka III will not be ready for the early 2026 test with BGR, necessitating a postponement. This was first announced on Tuesday at the first of these EIS consultation webinars, and notice of the postponement is posted to our website. Constraints have slowed our development timeline, and we cannot deliver a sufficiently tested vehicle by the planned date. Our team appreciates the time and effort BGR has invested in this EIS, and we look forward to continued collaboration. During today's webinar, we certainly welcome questions, ideas, and feedback to strengthen our eventual testing and monitoring plans. But we understand that there may be some questions around the postponement, and we ask that those be held for the discussion section that Becky referenced at the start.
Thanks, Jason. Yeah, so for clarity, the EIS that we're discussing today is the test that we're discussing today has been postponed. So while all of these things are still very relevant, because we're working together with BGR on that postponement and what that means, we do understand there might be questions about it. So looking forward to having that discussion at the end. So for now, I will pass things over to Christian from BGR, who will introduce himself and open our presentation today. Christian.
Yeah, thank you very much, Becky, and good afternoon to everybody, and thank you for joining this webinar today. My name is Christian Müller. I'm head of BGR's sub-department on marine resource exploration, and thus I'm responsible for the exploration activities of BGR in the Indian Ocean and also the Pacific Ocean. BGR is subordinate to the Federal Ministry of Economic Affairs and Climate Action here in Germany. Before we will dive into more geological and technical issues of the planned test, I will briefly provide you with some background information, and therefore just go through a few slides to begin with. BGR is a central geoscientific authority in Germany with more than 50 years of experience in marine research. We are state contractor at ISA since 2006. We are holding the exploration license on polymetallic nodules on behalf of the German government. And we have a well-analyzed contract area where we did exploration now for 18 years. And for this test, we are partnering with Impossible Metals, a US-Canadian startup company established in 2020 with a mission to harvest and process critical metals from the seabed while protecting the environment. The aim is to deliver innovative mining solutions with minimal environmental footprint. And therefore, what you will learn later, they developed an adapted autonomous underwater vehicle with artificial intelligence controlled selective nodule pickup capabilities. The aim of this webinar is to introduce a completely new technology from Impossible Metals for nodule harvesting, to provide insight into the regulatory framework for testing, and also to discuss the aims of Eureka III testing and monitoring the plans we have prepared and documented in the EIS. To showcase also the test location, its characteristics, and the expected impacts of testing, to provide technical, scientific, and logistical information related to the test and its monitoring, and to allow sufficient time for questions, input, and discussion. So our plan is to present approximately 1 hour, and then we have 1 hour left for questions and answer. And we hope to collect some ideas and suggestions for improvement of the EIS and the project in total. What we will not do during this webinar is to discuss political viewpoints on deep sea mining, and especially also viewpoints from states or the ISA. This is not the topic of the webinar today. Then some few words on the regulatory context. All activities in the area are governed by UNCLOS and in accordance with Part 11 thereof. The exploration activities are governed by appropriate ISA regulations, and they are, for example, ISPA 19 C17 for the polymetallic nodule exploration, all associated with rules, regulations, and procedures regarding also the exploration contract we have. Second important regulation is ISPA 25 LTC 6 revision 3, which is actually the draft mining code, and which covers also testing of mining components, and these require the submission of an EIS. Here in Germany, we have also national legislation which is the Seabed Mining Act, and this covers prospecting and exploration and assures compliance with national and international obligations. The EIS is governed by Annex 3 of ISPA 25 LTC 6 revision 3, where an EIS template is included for reporting the environmental impact assessment undertaken during the exploration, and also guided by ISPA 29C CRP1 and its draft annex, ISPA 24 LTC VP1 at 1. The process is informed by the draft guidelines for an EIS ESPA 27C5. You can find all these documents on the website of the International Seabed Authority if you want to dive into more details. Since we have a rather small scale test, we will talk about this later again. We see no socioeconomic impacts of the test presented here. The EIS therefore includes descriptions of technology used, available baseline data, expected impacts of the project, the test and monitoring plan, and consultation activities. Some milestones to present, which we have taken this year. In early August, the German Federal Ministry of Economic Affairs and Climate Action supported the test carried out by BGR at Impossible Metals. At the end of August, we notified the ISA Secretariat about the planned test, and due to the national legislation, we submitted the EIS to the national authorities who are involved in the national endorsement. In early December 24, we got the approval obtained from the German national authorities who were involved. And in late December 24, we submitted the EIS to the ISA Secretariat. We started then the public consultation on the 20th of January in 25, and this consultation period is still open until the 2nd of March 25. And this includes also the two webinars, the one we had on Tuesday this week and the webinar we have today. We will then submit a revised EIS based on the input we received within that period to the ISA, and this is planned for April. And the test, as it was already mentioned, is postponed, and we will go and plan for a test in 27-28, but this needs some consultation before this can be finally approved. Yeah, that's all for the framework. Thank you very much so far. And now we will go into more details, geological details first, and therefore I will hand over to Annemiek Fink from BGR. Thank you.
Okay, thank you, Christian. If you can stop sharing your slides, yes, then I can bring up mine. Okay, I hope you can all see this. Yes. Okay, so good day, everyone. It's a pleasure for me to be here today. My name is Annemiek Fink. I am the coordinator of the polymetallic nodule exploration group here at BGR. I'm actually a biologist by training, but have been working here with a bunch of geologists for the last 20 years. And I've been mainly responsible for the writing up of the EIS. So it's time now to dive into the content of the EIS and to take an especially deep dive into the BGR contract area and the activities that we are planning there in the framework of the Eureka III test. Which will now unfortunately occur somewhat later than planned originally. So I will show you some of the characteristics of the test area first. Then Jason and Becky will present the technology and the test plan, and I will return with the monitoring plan. So this map shows the locations of the present 17 contract areas for nodule exploration in the Clarion Clipperton Zone of the Northeast Pacific in blue. And the BGR contract area is in white, which actually consists of two parts that together are about 75,000 square kilometers in size. The BGR signed its exploration contract with the ISA in July 2006 and extended its contract for another 5 years in 2021. So we've been exploring for 18 years now, and the contract terminates in July 2026. Provided that there is political support for another extension of the contract, we will be applying for another 5-year extension at the end of this year, which would, of course, also be a prerequisite for a Eureka III test in 2027 or 2028. During our exploration period, we have carried out 11 campaigns with 5 different vessels, shown by the blue dots along this timeline here. Additionally, 3 research cruises in the framework of the European Mining Impact Project also carried out valuable environmental work in the BGR contract area, and those are shown by the green dots here. Collectively, we have obtained large amounts of data and samples that shed a lot of light on the geological and environmental systems associated with this part of the deep sea, probably making the BGR contract area one of the best analyzed areas of the CCZ. The general objectives of exploration as stipulated and regulated by the ISA are to carry out economic assessments of nodule deposits. So that includes mapping, sampling, studies of mineralogy and geochemistry, and of course, resource evaluation. We need to carry out environmental baseline studies, which includes oceanography, biodiversity, sediment properties, and fluid chemistry, amongst others. We need to carry out environmental impact assessment, which is basically the monitoring of small-scale impacts from disturbances and prototype collector tests. And then it also includes development of metallurgical extraction methods, industry cooperation for development of mining technology, and capacity building in the form of training of candidates from less developed countries, either at sea or in the research facilities of BGR in Hanover. So the 2 objectives that are shown in bold here indicate our legal obligation to carry out and monitor tests of mining systems and components as presented to you in the EIS and during this webinar today. This topographic map gives you an idea of what a typical contract area in the CCZ looks like. This is our eastern contract area with a size of about 56,000 square kilometers. So that's about 1/6 the size of Germany. Using ship-based multi-beam and backscatter, it's possible to resolve about 300 seamounts in this area, which are indicated in gray here. But in between, there are also extensive flatter areas in which the seafloor is covered either by large nodules, which are shown in blue here and cover about 9% of the area, or by small nodules, which are shown in yellow here and cover about 64% of the area. So based on this coverage and a slope angle of less than 3 degrees, potential contiguous mining areas could be defined, as shown in red here, that cover at maximum about 20% of the area. Our exploration work up to now is focused very strongly on 3 of these areas that we call prospective areas. And for the Eureka III test, we chose a flat locality in one of our best analyzed areas in prospective area number 1. I've included this short 3D photogrammetric video sequence, and I'll just see if I can start that. Yes, there we go. It's a typical flat part of the CCZ abyssal seafloor covered by large nodules, just to give you an idea of the expanse of the resource. These nodules have a size of about 5 to 6 centimeters. There's a coral coming by. And as you can see, they really lie very closely packed, almost as though they are paved on top and partly within the seafloor sediment. So as we fly over this particular field, you will notice that there are not many visible animals down there, with megafauna densities of just around 1 animal per square meter only. But of course, there are huge amounts of tiny microscopic animals, such as worms and crustaceans, nematodes, living in the sediment and in the nodules, which we cannot see here, but they are responsible for the very high benthic biodiversity that's typical of the CCZ. And here on the left, you can see a nice anemone. All right, so the goals of the project we are presenting today are for Impossible Metals to test and prove the technical feasibility of a single Eureka III AUV, and for BGR to carry out the environmental monitoring around the test, to analyze impacts and effects of the test, but also in comparison to the impact area of GSR's Britannia 2, which was monitored by BGR in collaboration with the Mining Impact Consortium in 2021. So here on the left is a map of the western part of our prospective area number 1. It has dimensions of about 20 by 30 kilometers, with the Britannia 2 trial site up here in the north, and its reference area as indicated by the oval shape over here. We've picked a trial site for the Eureka III test within this square area here, which makes use of the same reference site as was used for Britannia 2. So the map in the center here shows the trial sites in more detail, and this stripe in the middle reflects a seafloor area for which we have high resolution bathymetry available. So the test will occur in this nice flat area here, labeled as E3TA. It's about 4 kilometers away from the reference site at a water depth of about 4,130 meters. And it's actually also quite close by to a dredge disturbance experiment area from the project Mining Impact in 2019. So this test area that will be cleared of nodules during this experiment, during this test, only has a size of about 1.5 football fields. So it's tiny, to remain precautionary on the one hand, but obviously also to give us the opportunity to monitor impact and change on the other hand. The green lines over here and the white dots, they represent the locations of yearly faunal time series analyses that we've been carrying out since 2013. That have provided a lot of insight into the very high spatial and temporal variability that is typically observed in these deep sea environments. And the green arrows over here, they represent mooring sites that have registered hourly current speeds and directions at the seafloor over 3 consecutive years. So within this entire larger area, we feel that we have a unique situation in which we can compare impacts caused by different types of technologies, and also to use the lessons learned from previous experiments, for example, regarding monitoring technologies and strategies for this Eureka III test. So this is the thin stripe of high resolution seafloor bathymetry that I showed before, and the test area will be right in the middle here. It's an animation which I'll start. just to show you sort of what the topography in this larger area looks like. So these data were obtained using BGR's deep towed acoustic system, and the resolution is about 1 meter. The width of the area shown here is a few kilometers, 5 or 6 kilometers, but the contours just represent 2 meter contours. So what you see is that the area is definitely not flat. We have a lot of larger depressions, round depressions of 100 or so meters in diameter. We're now changing view to a backscatter view, providing some information on the roughness of the seafloor. And here we end back at the Eureka III trial site. And the Petania site is actually to the northwest over here. I'll just add, as the topic of cultural heritage is becoming more important in the context of marine mining, that we can also use data such as these for high resolution screening to make sure that there are no archaeological objects such as ship or aircraft wrecks in the trial area or its surroundings. Unfortunately, in this webinar, I simply won't have the time to go into details on the baseline oceanographic, biological, and geochemical data that we have gathered and analyzed throughout the years. But these are extensively described in the EIS, so please do browse through those chapters if they are of interest to you. What I have done on this slide is to give you an impression of the number of peer-reviewed publications which have appeared based on data from the BGR contract area since 2011. So we've registered 113 peer-reviewed publications. Half of those cover biological topics. And I think it's quite interesting to look at the history of our publications. For example, the number of geological publications has remained relatively stable during time, but you can see in green that the number of biological publications has greatly increased. So that does reflect how the focus of our exploration work has also changed during time. These publications have not only arisen from the BGR, but have resulted from numerous collaborations with renowned scientific institutes in Germany, but also abroad, as shown by the logos down here, and especially also from the Mining Impact Project. All right, so that's enough from me for now, and we'll change to Jason and Becky for the technology and the test plan.
Thanks very much, Annemiek. I know that the baseline information there's just so much of it, as you'll see if you go into the document. So certainly, although Annemiek didn't have time to go through that at this point, she is more than willing to answer questions about it once we get into that section. I know she's very knowledgeable about it. There we go. Okay, so Jason and I will now talk about the Impossible Metals side of things, the technology. So an introduction to our idea for our whole system to start with, for anybody who's not familiar, getting into the specifics of the Eureka III AUV, and then the test plan. And Jason and I are both hailing from Ontario, Canada this morning, so it's an early one, but we're very happy to be here with you.
Yeah, Becky, why don't you jump in? So our first slide is just an animation showing the overall operation.
We are developing autonomous underwater vehicles that are launched from a ship to the ocean floor, where there are vast fields of rocks called nodules that are rich in metals that are critical for low-carbon technologies, like batteries. Hovering over the ocean floor, artificial intelligence uses cameras and robotic arms to pick up each nodule individually, minimizing sediment disturbance and avoiding visible life, while leaving behind a percentage and pattern of nodules to preserve biodiversity and ecosystem services. The collected nodules are stored on board, and once the vehicle is full, it returns to the ship. The recovery crane is designed with motion compensation for fast docking, giving the vehicle a stationary target. Once on board the ship, nodules are offloaded and the battery is swapped before the vehicle's next trip to the seafloor. A key part of this system is that the fleet of underwater vehicles remains at sea. As one ship is filled with nodules, another arrives to continue the collection operation. Our highly scalable fleet is designed to reach the high production levels required to meet market demand.
Thanks. So we like to share that at the start here, just because the architecture and approach that we're proposing with our technology is fairly different than the architecture and approach from systems that are track-based with suction heads and riser pipes. And so it gives an overall view of really how the system is fundamentally different. There really are two or three key enabling technologies that are built into our system to enable this approach. The first is the vision system at the front, where we're able to identify the nodules, track those nodules, identify life, and then allow us to have exclusion zones around those macrofauna that are identified. The second is then the Delta arms. Traditional underwater robotic arms are really designed for high dexterity, high strength operations, where our arms are more akin to industrial automation pick and place operations, and so that was novel for our system. And then lastly, as we're adding weight to the system in order to stay hovering over the seafloor, the buoyancy engines built into the vehicles themselves is what maintains our neutral buoyancy as we're collecting nodules, and then ultimately that buoyancy is what drives the vehicles up to the surface.
At Impossible Metals, we are developing autonomous
So in our testing from November, we were able to demonstrate Eureka II. So this is the predecessor to Eureka III, which is smaller with certainly fewer arms, but works off the same principles, where we have the vision systems that you can see on the bottom, tracking the nodule representative nodules, not actual real nodules, in the harbor at our test site, and then as those representative nodules come into reach of the arms begin to engage with those, pick them up, and aim to minimize the amount of sediment disturbance that's being created by the process. And then this next set of imagery or video is from our tow tank. This is in our lab, where we then placed some plastic starfish representing the megafauna that allow us to really show the capability of the system to identify those and then set exclusion zones around those identified creatures to tell the system to not pick up the nodules that are close to those life. So now getting a little bit into Eureka III. It is a 6,000 meter rated system with a payload capacity of 4 tons. Rather than the 3 arms that you saw in Eureka II, it will have 11 arms, and really is about a 20-foot shipping container, so like an ISO container in size. The dry weight of the system is 11 tons. The battery capacity is about a 90 kilowatts, so it's on par with what you'd have with a long-range sedan electric vehicle. And we use 6 thrusters, 2 vertical and 4 horizontal on this system. Really, when we started with our design and our approach a number of years ago, we said, look, we want to improve the environmental impacts for this collection process to collect the critical metal needed for electrification. But really stepped back and said, okay, fundamentally what we're needing to do is get the nodules from the seafloor to the shore. Let's throw away any preconceived ideas and really develop the system from the ground up. How can we do this in the most economic way? And so building up a number of different solutions based off of a variety of ideas, we were able to analyze those based off of their economics. And then ultimately, as we've solidified and worked towards this solution, we continue to drive design decisions, things like how fast the vehicle is traveling, how many arms per vehicle, based off of those economic factors to allow us to not only achieve what we think could be superior environmental impacts, but also superior economics to alternative architectures. So the vehicle footprint is, as I mentioned, a shipping container in size, and we've really defined that for convenience of transport and handling. The system is also very modular, so the same arm designs that we've been able to test with Eureka III are able to transfer, that we've been able to test with Eureka II are able to transfer over onto Eureka III. Similarly, much of the buoyancy engine concepts, as well as the electronics themselves for driving the overall system, that is all testing work that is done within Eureka II and is modular to move over to Eureka III, and then ultimately to a potential Eureka IV down the road. One of the things that we've really focused as well on is trying to move very quickly, ensuring that we're able to iterate and test, and that's part of why we are so interested in this work with BGR to evaluate the system. So there are some modifications to Eureka III that have reduced the size based off of some of the latest optimization work from when the EIS was first submitted. In particular, the number of arms has reduced from 16 down to 11, and the size in terms of the capacity of the vehicle has been reduced from a 6.6 ton to a 4 dry metric ton payload for the system. Because of cost efficiencies that we were able to identify with the buoyancy system, it has allowed us to hit the same economics, but with smaller vehicles driving this change. And I'll pass it over to Becky to talk a bit about the testing plan.
Thanks, Jason. So one of the things that we've done since the beginning of Impossible Metals is have these discussions called scientific roundtables. And there's a growing group of deep ocean scientists who have very generously given their time to meet with us a few times. When we have questions about the thing that we're working on at the time. And so very early on in the process of discussions with BGR about a potential test, when we were thinking through what a testing plan might look like, we I had all these ideas, you know, like, well, you know, we can program it to take different percentages of nodules. We can program it to do patterns or random so I went into this meeting thinking I was going to get feedback that, yes, we want to see you try all these different things. And it was absolutely the opposite very quickly. And I think there's folks here today who were in that meeting. They said, please slow down. What you need to do is do something repeatedly and get very good measurements of it. So try to just do one or two things well. So that was the first piece of feedback, and it was very well taken. And the second piece, among a variety of feedback we received, but these two in particular were quite impactful. If we're going to have a difference in the percentage of nodules removed in different parts of the test, that difference needs to be quite wide. If we want to have the best chance of detecting a difference in the impact of those modes. So those are the two pieces of advice that we really that made a big impact. So now I'll talk about what we ended up with. First, I need to define what a cycle is for you so that we can speak the same language. A cycle for one of our AUVs is the launch and descent down to the seafloor, the collection time, the ascent, recovering the vehicle, any battery and maintenance and offloading of the nodules, and then getting it back in the water. So that's one cycle. We ended up with a plan of 20 cycles over 4 days, and each time it runs one of the lines in this image. So it starts at one end, runs to the other end of the line, and then it goes back up to the ship, and then it comes back and starts again. This is not to scale, by the way, so it was what fit in this box. But you'll see that there's two different lengths of lines, and those represent different percentages of pickup. So the shorter lines, there's 10 shorter lines, and those are 90% pickup. And the longer lines are 50% pickup. So quite a big difference there, in a 40% difference. I will note that our economic model is estimated at 70% pickup, so leaving 30% of nodules behind as a hard surface for the ecosystem. Now, that is a true assumption at this point, and the actual number, if there was mining plans that were to go ahead, would really depend on an environmental impact assessment that's carried out, and recommendations of the scientists working on that. So but at this point, as a first go, looking at that 90% and 50%, so that not only can those impacts be monitored during the test, but also in the future to go back and see what longer term impacts look like, and if there's a difference in longer term recovery. Okay, so that's all I have to say on the testing plan, and at this point I will hand things back over to Annemiek.
Okay, thanks Becky and Jason. And I will get back to my slides. Right. Okay, so I'll start by providing a bit of information on the plume modeling work that is being carried out. So Impossible Metals commissioned a study to DHI in order to model the behavior and far-field impact of the benthic sediment plume caused by Eureka III, according to the test plan that Becky just presented to you. So one key purpose of modeling is to use it as a basis for the monitoring plan, and after that monitoring has occurred, to use the measured data to verify or adapt the model and inform future modeling. So this is an iterative process during impact assessment. So in summary, DHI's Mike 3 FMMT model was used as a basis. Robust input parameters such as high resolution bathymetry, near bottom current data, sediment parameters and nodule size parameters were provided by BGR. Two different scenarios were modeled. One for a situation in which there is a predominant but variable southeast current flow, which is most typical for the area throughout the year, and then one for a stronger and more unidirectional southwest current flow, which, based on the available data, more closely reflects the conditions in the month of January when the test was originally planned to occur. Nodule size distribution was found to be an important parameter, as nodules will be individually pulled out of the sediment. So the amount of sediment removed and put into suspension is assumed to be dependent on the surface area of the nodule. For this modeling, an assumption of a 2.2 millimeter thick layer of sediment removal with each nodule was made, which might be on the low end, and it's probably the biggest assumption in the model at the moment and remains to be tested in the field. So based on all of these data and assumptions, an average spill rate of 0.05 kilograms per second was determined. And with this very low spill rate, particle concentrations will typically remain relatively low. And so no flocculation is assumed during plume production and dispersion. So a density plume is not anticipated to develop in this case. This is an animation of the resulting modeled suspension plume. Let me start it, right? So it obviously the plume develops mainly behind the collector. This is for the January scenarios with a southwest current flow. So the collector is moving from the southwest into the current to the northeast, and the bulk of sediment suspension then remains very close to the seabed, and it starts to drift off with the currents towards the southwest. On the right, you can see the sedimentation footprint in the top diagram and the total suspended sediment concentration in the bottom diagram. So by now, production has finished. You can see the plume moving off, still towards the southwest. Concentrations are falling, basically down to values of 0.1 milligram per liter, as shown by the purple color here. And 0.01 milligram per liter is the background concentration, so the no change concentration. At the top, the sedimentation map, what you can see is that the bulk of the sedimentation, which is greater than 1 millimeter in depth or in thickness, which is shown by the dark brown color here, all remains basically within the test area itself. Slightly outside of the test area, we can expect sedimentation between 0.1 and 1 millimeter, and then beyond that, the sedimentation is less than 0.1 millimeters, which is no longer actually physically measurable and is assumed to have an insignificant effect on fauna. So the test is finished, or we're 7 days after the end of the test now, and you can see that the suspension has almost disappeared out of the area, and we have a maximum sedimentation up to 700 meters away from the test area, but as I said, with a very, very low sedimentation here, and most of the sedimentation remaining in the test area. So as a summary, 95% of suspended sediment is redeposited on the seabed within 7 days post-collection, and 93% of that material remains in the mined area. plume concentrations fall to no change thresholds within 7 days post-trial, and sediment suspension actually remains very close to the sea floor as well, so within the upper 5 meters of the sea floor. A sensitivity test was carried out by doubling the spill rate, thus increasing the amount of sediment that's being resuspended. But due to the sort of no flocculation suspension nature of the plume, the reaction was found to be linear to that already shown. So in simple terms, the values will double, but the spatial impact of the plume remains very similar. So moving on to the monitoring plan, we have set a couple of overarching hypotheses for the Eureka III trial that we want to test with the monitoring plan. First of all, that Eureka III successfully avoids picking nodules with visible megafauna. We want to show that selective nodule pickup reduces habitat degradation in harvested areas compared to collection systems using suction pumps. We want to show that plume particle concentrations can reach background within about 700 meters of the test site, and that sedimentation greater than 1 millimeter is only expected in the test area itself. So as already mentioned, the test is now scheduled for a later date in 2027 or 2028, depending strongly on when we can actually secure a suitable research vessel, such as the German research vessel Sonne or something similar for the monitoring work. Whatever the case, Impossible Metals and BGR will be on 2 different vessels. And depending on the facilities and the expertise on board, we feel that at least 16 days would have to be devoted to the Eureka III test monitoring. And these include at least 4 days for baseline sampling and sensor deployment before the test, 4 days of testing and plume monitoring, and then 4 days of post-impact sampling and 4 days of sampling in the reference site. As far as long-term monitoring is concerned, one revisit of the test site would be possible within the extended contract period, for example, in 2029 or 2030. Probably then also in combination with a monitoring of the Patania 2 site, but further opportunities obviously cannot be evaluated at this stage in time. This great cartoon shows the monitoring survey setup that was used during the Patania 2 collector tests in 2021. And thanks very much to GSR for allowing me to use this slide. And this setup proved to be quite effective in terms of management of simultaneous operation of equipment from the 2 vessels, but also in terms of data retrieval and sampling strategies. So this scheme, based very much on strategies developed by the Mining Impact Project, sort of functions as a blueprint for the monitoring of Eureka III. So what we can see is basically an AUV flying at about 5 meters above the seafloor, collecting photographs, which can then all be stitched together. And in this way, it's possible to get a photo mosaic of the entire test area, in which you can really see quite well where the nodules have been removed, how there are changes in the microtopography of the seafloor, where sediment has been removed and redeposited, and how the megafauna distribution has changed as well. So that was important, and the AUV furthermore flew along predefined lines, also into areas outside of the test area to have a look at ranges and thicknesses of deposition caused by the sediment plume. It's also good to have a series of moorings placed around the test site with oceanographic equipment. And a lot of these small sensor platforms were placed on the seafloor by ROV. So these contain basically different types of sensors as well, acoustic and optical sensors, to be able to measure the particle concentrations in the sediment plume. So they were placed at strategic positions around the test area, but obviously also especially in the direction of expected plume dispersal. So the ROV is a very important piece of equipment to place these sensors on the seafloor, but also obviously for stuff like biosampling, geochemical sediment sampling, visual inspection of the plume, and things like that. The AUV was also equipped with turbidity sensors, and during the test itself, it can be made to fly in a circle around the test area at different heights above the sea floor. So in this case, it was 5, 10, and 30 meters above the sea floor. And in this way, it was able to really monitor the spatial, vertical and horizontal, but also the temporal change of the plume as it was being developed, which is great because you never really know in which direction the plume is really going to move. And in this way, it's always possible to register it. Yes, and then we also had a CTD that can be made to be lowered into the plume to take water samples. So a lot of different fancy equipment that was all used at the same time. As an example of the lessons learned from the Britannia 2 tests, I'd just like to draw your attention to this study by Gazis et al., which was published about 2 weeks ago in Nature Communications, and provides expert advice on how to plan and execute future AUV and plume sensor networks for monitoring purposes. For our purposes, it has, for example, shown that high-frequency acoustic ADCP, such as aqueducts, and especially optical turbidity sensors, are the most sensitive and effective for registering our expected low particle concentrations and smaller particle sizes. So I've listed the minimal requirements for a good monitoring survey in terms of required equipment and deployment times in this table. We feel that we'd need at least 3 long AUV surveys, 2 for photomosaicing, 1 before and 1 after the test, and 1 to measure plume turbidity during the tests. Obviously, an ROV is a prerequisite. We would need 24-hour operations to deploy the platforms for the visual inspection and for all the different types of sampling that are required. Moorings, at least 4 and at least 10 plume sensors on platforms would be required on the sea floor to measure the currents, the plume concentrations, and maybe also the particle sizes. We feel that oxygen microprofilers and benthic chambers are required to measure oxygen fluxes in the sediment and oxygen consumption by the benthic organisms. Hydrophones would need to be placed on the seafloor to measure noise, and the CTD would be able to take water or plume samples, especially for trace metal analyses and for the analysis of potential toxicity. Obviously, sediment samples will be required also to have a good look at the fauna and the geochemical changes in the sediment. So the best would be to place those in a direction with a gradient of impact. On the right here, bottom, I've shown how box and multi-cores could potentially be placed. We'd have to basically sample the 50% and the 90% nodule pickup areas, as well as plume deposition areas. And obviously, these are very, very closely packed to each other. And the same applies basically for the plume sensors. We would have to place them as close as we can possibly get to the test area in order to basically be able to measure anything at all. So this is my last slide, and I've just come to the expected sort of larger scale outcomes of the test and its monitoring. Obviously, we want to offer a sound scientific monitoring and evaluation of the scales of impacts. First of all, the physical impacts, but then hopefully also the effects on the fauna. We will be testing state-of-the-art monitoring concepts and strategies, which aim at improving those. So technological improvement refers to obviously improvement to Eureka III itself and its pickup system, but also to those monitoring concepts. Plume model validation is a very important aspect to improve prognoses. We would like to reduce uncertainties related to impacts through this type of monitoring and research. And in the end, obviously, we hope that data like this can contribute to ISA regulations and guidelines. So eventually, I think results like this are likely to be important inputs to future EIAs for the tests of integrated systems at a later stage. And that brings me to the end of my presentation. Thank you very much.